Welcome everyone to the third lecture of Distributed Systems Technologies. Last time Andrea talked about monolithic applications and how we can split up those applications. It was sort of a continuation of what we talked about in the first lecture, namely how to apply the tools of abstraction, generalization, and layering to decompose a monolithic applications into service consumers and service providers at the most general level, and which technologies we use to let them talk to each other. So we talked about RPC, talked about remoting in general, and we found that there's sort of this archetype for, or this blueprint for remoting technologies, whether it's RPC or whether it's web services or whether it's RMI. You have these principal components involved that are fairly equal throughout any type of remoting application. And we talked about how to interface different services with each other via this API gateway architecture. And we talked about the way that API gateways become this monolithic layer that sits on top of all microservices and then knows about a lot of microservices, needs to know about a lot of different protocol implementations, and then sort of becomes this chatty interface. And then we learn what we can do about that. So in that sense, we're going to continue some of that in coordination algorithms. So we'll talk how we actually coordinate distributed systems. And there are a lot of different coordination problems. We'll pick out two in particular because I think they're interesting and they're very relevant. So distributed consensus is something that's relevant for a lot of different things in distributed systems. And I promised we'll talk about two-phase commits. And I want to talk about delegated authorization and OAuth in particular, because I think that's a very relevant kind of problem in today's web applications and today's software landscape in general. And then we'll talk about, because that's relevant for the second assignment, about application frameworks, application servers, and how dynamic features are implemented in these frameworks. So we'll learn in particular about inversion of control, the mechanism, and how it can be used to implement certain things like transactional features or container managed locking, things like that. All right, so let's dive into coordination algorithms, and let's start with distributed consensus. So you know this from distributed systems course. Distributed consensus is the problem that all nodes in a network have to agree on some information. So imagine database consistency. So consistency in the sense of the CAP theorem, as we talked about, so that when you write to a replica that and read from another replica that you actually get the same value. So when you write something to a database, you want to make sure that all nodes in that database cluster agree on which item to serve next. Leader election is one type of consensus, distributed consensus problem. So you know this from distributed systems. Often you have situations where you need one person or one node to be the leader. Also, for example, in a distributed database, you need one entity that's the authority for propagating writes, for example. Clock synchronization is a fairly well-known problem. Blockchain is also a type of distributed consensus problem. Some well-known algorithms for distributed consensus are two-phase commit, which is a very basic form of distributed consensus, which we'll talk about, and more complex implementations like Paxos and Raft. So we're not going to go into this because these are very complex algorithms, but they're useful to have heard about. So let's talk about distributed transactions. We talked about them in the first lecture, so it was just a recap. There's this problem that you have a monolithic database split up onto different servers, and now when you do a transaction across several database servers, you need some way of making sure that you have an atomic commit. So how do you do that? Specifically, what you do, when you have failures or when database servers don't agree on a specific commit. This is where two-phase commit comes in. And at its very basic form, you have a coordinator and you have some participants. So in this case, they're just databases. We'll talk about a more general view of distributed transactions and the components involved in a second. So two-phase commit, as the name suggests, is split into two phases. There's the voting phase, where when you begin a transaction, the coordinator starts recording the transaction commands, or rather the database client provides the transaction commands, and the coordinator asks the participants whether they are okay with executing these operations. So the coordinator queries the participants whether they want to execute and whether they can execute this transaction. So for example, they would say no if a database constraint is violated. What's important in two-phase commit is that the participants have two components, namely an undo log and a redo log. This is to recover from failures in case the node goes down during the two-phase commit procedure or during the transaction procedure. And it's important to be able to roll back the transaction if something goes wrong at a different participant. Okay, so the coordinator asks every participant if it's okay to commit. If everyone says yes, the coordinator will send another commit message to all the participants, and then the participants will actually commit this transaction and free the logs. If there is some failure during voting, either because the participant says, sorry, I can't execute this transaction because a database constraint is violated, or the participant suddenly runs into a failure, the coordinator will send out a rollback command to all the participants. The participants have to run their undo commands. So they need to roll back and they need to free all the locks. So database systems typically have like a large lock table where you have named locks that associated with a specific record that is locked during a transaction. So there's this, as I said, it's a quite simple protocol. There are some limitations associated with two-phase commit. Namely, it relies on participants having a stable storage with write-ahead logs. So a participant needs to write ahead all of the entire commit before it's actually checking or trying to execute the commit on its data structures. Because if the node goes down before executing the transaction, it needs to be able to recover from that failure and then be able to remember what transaction to execute, or what commands to execute in that transaction. It's assumed that the write-ahead log is never lost. So if a participant writes the write-ahead log to disk and that fails because of some reason due to disk corruption, then we can't really do anything against that. And we assume that nodes don't crash forever. So if while the coordinator waits for an acknowledgement before sending the commit or the rollback command, if the coordinator and one of the nodes go down and never get back online, the other nodes will be stuck in a loop or in some blocking state, probably forever. So this is why. So because it's a blocking protocol, this issue may occur. The immediate solution to this issue that a node may go down while a commit is happening and the coordinator can't be sure whether the commit was actually successfully executed, the immediate solution is to introduce another phase where we do like a pre-commit where all the commits are done, and then there's another commit acknowledgement. So adding this additional phase adds some resilience towards failures. So in general, we can kind of generalize this distributed transaction through three main components, which are also the names typically used when we talk about distributed transactions. A resource which holds the values to be modified or accessed. So a resource can be any type of component. typically we assume it's like a database or something, but it can also be like a very heterogeneous microservice that does something, that needs to do something transactionally. The resource managers implement the consensus protocol and interfaces with the transaction manager and the resource. So in case of a database resource manager, that resource manager knows how to execute database commands. And then there's the transaction manager, who's the leader in this network of resource managers that coordinates the transaction. So could be statically configured, as it is in JTA, for example. We'll talk about JTA in a second. But could also be elected. So in some situations, you may say that, okay, all resource managers are equal, and you want to elect one of the resource managers as a transaction manager. And specifically in two-phase commit, we can model each state that a resource manager can be in from working, which is, okay, it's waiting for transactions to appear. It can be in the prepared state. So this means that, okay, it's said to the transaction coordinator that it's ready to execute that transaction, and then it can come into the state either committed or aborted. So for JTA in particular, which gives you, so we talked about Java Transaction API, and which we'll be using in the second assignment. It's this abstraction of Java EE for transactions and distributed transactions. And how it does that is it uses OpenXA, which is this architecture for distributed transactions. So it sort of implements this picture that we saw previously. It's kind of a specification, and it describes this interface between the global transaction manager and the specific application. And as I said, JTA builds on this extended architecture. And as a homework for the lab, you'll look into some of the JTA components that look very similar to this and describe them in one of these theory questions. So let's talk about delegated authorization. OAuth has become such an important part of today's web and application infrastructure in the web. So what is delegated authorization? The example that's often given is which is not very common in Europe, but in the US it's very common to have these valets. So you bring your car to a valet, and instead of parking yourself, the valet takes your car and parks it for you. But for that, you need to give the valet a key to your car. So the idea is that you don't give the valet your key that can unlock everything. So your key would unlock the door, start the engine, but also open the trunk, open the glove box compartment, and whatever else locked elements you would have in the car. Whereas the valet key just opens the doors and starts the engine. So this is kind of the core idea of delegated authorization, is that you only give, you delegate access to something so that entity can access a resource that belongs to you, in this case the car, on your behalf, but with limited access. So why was this invented, or why was this an issue? So before we kind of came into this idea of mobile applications and web apps in general, we had basically everything in the web worked with web form authentication. So a lot of us grinded our teeth in developing this in PHP. So we had some login interface where you'd send the credentials of a user to some backend server. The server would be responsible for hashing the password, verifying the hash, looking up user info in the database, and then looking up the authorization info. So what is that user allowed to do? And then the browser would set some session ID, and the server would know about the session ID, so would know that the user was logged in before. This is fine for simple scenarios, and if you don't have any intermediaries between your backend application and your front-end application. But in modern scenarios, it's often the case that you have some service, let's take Twitter for example, and you have applications that want access to specific APIs of your Twitter account. So Buffer is like a Twitter application where you can schedule tweets, and those tweets will then be posted online at specific times that you specify. So you won't be physically present to post a tweet, but Buffer will do that for you. Consequently, it needs write access to your feed. So it needs to be able to log into Twitter for you, post a tweet when you're not here. So the goal or these modern scenarios require that client applications have access to a user's resource and can access them on a user's behalf using what we call access tokens. So an access token is kind of an ephemeral password. So instead of giving the client application access to everything and specifically our credentials, we only give them access to like a token that's valid only for the specific client app that has attached to it certain permissions of the resource. So let's take a look at an example of bad delegated authorization. So banking applications are often a good example of how not to do things in the web. Specifically, they seem to be behind with a lot of web technologies, and in particular OAuth. So if you've ever ordered something bought something via Sofortüberweisung, so it's a Sofortüberweisung, for those who don't know, is a payment provider. Basically, what it does is it mediates a payment between you and some third party. And Sofortüberweisung guarantees to that third party that you executed the transaction. What it does is you give Sofortüberweisung your credentials in a page like this. So the page like this would open once you buy something on an online shop, click on Sofortüberweisung as a payment provider. This page pops up and you have to input your account and your PIN, and that is actually, those are the credentials for your e-banking application. Sofortüberweisung will log into that e-banking application and perform the transaction for you. It will then guarantee to the third-party provider that the transaction was executed because it executed the transaction for you. So you're actually handing over your account number and your password to Sofortüberweisung, who then log into your e-banking account. So I don't know, my feeling is that today they probably have some agreement with some of the banks, and they potentially use some backend APIs of the banking applications. I don't know. But when it first came up, they were literally using a web scraper in the backend to log into your banking account. So they'd have some component that would physically start a browser and like a headless version and then log into your e-banking account. So this is a good example of bad delegated authorization. So this is where OAuth comes in. The OAuth authorization framework is a specification. It's a very long and complex specification. And basically what it specifies is an approval interaction between a resource owner, which a resource owner would be you in the case of in the example of the valet. So you would be the resource owner and the resource would be the car, and some HTTP service, which in this case is the car. So by allowing the third party, which would be the valet, access to that application on your behalf. And let's look at some of the terminology that's used in OAuth before we look into a specific example. So you've probably all seen a picture like this or a page like this. So this is when an app wants access to some of your Google account information. And let's break down some of the terminology that OAuth uses for the individual components in this example. So the thing that that example app wants access to is the resource. So for example, it wants to view your basic profile info, it wants to view your email address. So those are resources. You are the resource owner. So oftentimes it's confused. Resource owner and clients are confused because often when we talk about clients, we think about ourselves. But in this case, the client is the example app. So the client wants access to the resource and you are the resource owner. Viewing or editing is what we typically call a scope. So a scope is not rigidly defined in OAuth. So a scope can be basically anything, can be a label or something, and different providers will implement scopes a bit differently. But essentially a scope is just specifying what you can do on that resource. Okay, so this is sort of a summary of the OAuth terminology. We'll talk about the authorization server and the resource server next, and we'll talk about access tokens, which are these ephemeral passwords. A grant in OAuth terminology is the type of interaction pattern that's used to exchange or to give the client an access token. So different ways that a client can get an access token and access a resource. And we'll talk about one in particular, namely the authorization code grant flow, which is arguably the most complicated one in OAuth. So let's look at this concrete example. So we have a user who's the resource owner. We have the client, like for example, this buffer app that wants access to a resource on a resource server. So in this case, it wants access to your Twitter feed. It wants to be able to write to your Twitter feed on the Twitter servers. And you have the authorization server, which is the central component to facilitate this exchange of delegating access from a user to a client. Okay, so let's start with the client wanting access to that specific resource. So a user has a browser, it requests access for a specific type of resource, and it will redirect the request to the authorization server. So at this point, the authorization server displays this page to the user and asks the user to authenticate themselves. So typically you're already logged in because you have some session open. So if you've ever granted access to an application in Google, for example, you know that you don't always have to log in. Your session is already stored, but essentially you have to authenticate yourself. The authorization server then requests the client authorization. This is just this mask that we saw earlier with the information that this client wants specific access to a specific resource. And it's important that you see the authorization server, you see the URL of the authorization server. So in case of Google, you would see the URL would be auth.google.com. In the case of Twitter, they have their own authorization server, which you would then see. So user clicks OK, yes, I grant the client access to that particular resource. And then the authorization server redirects to a callback URL that the client previously supplied. So we'll look at the callback URL in a second, but essentially when the client requests access or requests an authorization code from the authorization server, it provides a callback that the authorization server then has to call once the user has given the client authorization to access that resource. So now the authorization server redirects the user's browser to that callback, which contains the authorization code. So the authorization code is not yet, you can't do anything with the authorization code yet. So you can't access the resource yet. It's not a token. But what the client does with the authorization code is it exchanges the authorization code for that specific authorization and its client credentials for an access token and a refresh token. Okay, so let's break that down. The reason why you're not getting an access token directly from the authorization server is because you're redirecting, in OAuth terminology, something through a front channel. So the browser and the user are what we call front channel, and the client application and the authorization server, which is sort of hidden in this backend application, which is server-to-server communication, we call a back channel. So, and in general, we assume that a front channel is unsecure and a back channel is relatively secure. So everything that's secret is stored in a back channel, and everything that's, it's okay basically if that can be intercepted, we store in front channels. So there are some exceptions, but it's not worth going into that in too much detail. So essentially, you get the access token only if the client validates its identity with the authorization server. So this is what we mean when we say client credentials. This assumes that, or this implies that the client is registered with the authorization server before. So if you've ever tried to develop an application yourself, if you go into, you need to log into some development platform of the specific platform that you want to develop your app for. So in the case of Twitter, there's like dev.twitter.com. You have to go in there, log in, register a client application. You need to verify maybe an email address at least, and then you from the Twitter development platform you get client credentials, so they're secret keys. And now that the authorization server knows that you are the client that you're claiming to be with the client credentials and the authorization code, the authorization server knows that, okay, this user granted you, the client, access to that specific resource, and now it gives you an access token and a refresh token. I'll talk about the refresh token in a second. So now the client can go to the resource server, give the resource server that access token and say, here, this is the access token that's associated with that particular user, that authorization, and that scope and that resource. And then the resource server can give access to that protected resource. There's no rigid definition in the spec, in the OAuth spec, of how the resource server actually validates the access token and checks exactly which resource the access token grants access to. So there are different ways of implementing that. You could do that directly on the resource server. You could ask the authorization server every time. So there are different architectures and models that you can do that with. Okay, so why does the client need this refresh token? Access tokens are typically short-lived. So let's say 10 minutes. The reason is that once your access token gets lost, someone steals your access token, they would have access to that protected resource essentially forever, because remember, it's like an ephemeral password. So instead of having this access token live forever, what we do is we invalidate that access token after, let's say, 10 minutes, but we don't want the user to go through this grant flow every time. So instead, the client can go to the authorization server and say, remember me, these are my client credentials, and you gave me this refresh token, and with the refresh token, you can get a new access token. So remember, again, we're in the back channel. The client credentials and the refresh token are sort of safe on the client, and it can get a fresh access token every time it needs one. So let's look under the hood, what happens. So the HTTP, OAuth is all HTTP based. And the spec defines like how HTTP requests for specific things need to look like. So requesting an authorization code from an authorization server looks like this. So you would call the authorization server of Google in our example. You'd say the response type, what you want is an authorization code. You'd pass some client information. You'd pass the scope that you want access to. And you'd pass this callback URL. So in this case, you're calling the authorization server would call this URL after it checked the validity of the request. And you also add the state parameter. So because RESTful services typically don't keep any state across requests, it's important that we add this state parameter so we kind of know which specific flow these requests are referring to. The response that the client then receives via this callback is basically just the code and the state parameter. And then when the client requests an access token, it again calls the the authorization server. Now it wants this authorization code. It again supplies a callback URL that's the authorization server calls once it wants to give the client the access token. It again provides some client information, and then the response is this access token. So the authorization server would then call this redirect URI, and as a body would be this response containing the access token, And this is sort of the secret that the client needs to keep. Okay, so let's summarize. The authorization code grant flow is one way of implementing this interaction of getting an access token. And the ultimate goal is to delegate access to a backend application. So clients are registered with the authorization server with their client credentials. This is important, so that the authorization server knows about the clients. The clients ask the authorization server for these access tokens. And the access tokens are obtained by providing, as I said, the client credentials and the authorization code, which is the user granting the client access to the specific resource. So the authorization code verifies that. And the refresh token can be used with the client credentials to obtain fresh access tokens. There are other type of grants. So the authorization code grant flow is what we looked at. There's some other grant flows that I don't want to get into, but basically what I just want to show you is that the OAuth framework defines various types of workflows for different types of scenarios. And you can look those up in the spec. All right, so at the end I have a credit slide where I link to a talk that a lot of this information came from. So it's like a 1-hour talk, and he goes into details of different grant types and different views on this authorization code grant flow. So if you're interested in OAuth and OpenID Connect, which is sort of used on top of OAuth, then have a look at this talk. It's very good. Okay, so let's switch gears a bit, and we'll talk about application frameworks and servers and how we build enterprise applications with these frameworks. So if you remember, last time we spoke about the way that application frameworks try to generalize enterprise applications. So we learned that enterprise applications are typically made up of components, which we can see as more general versions of a service, and they have some communication pattern. So whether it's local calls or remote calls, that involves some API mechanism, some marshalling of remoting messages. You have persistence and transactions. All of these things can kind of be generalized and supplied by an application framework in a kind of general way. This enables code reuse and all the benefits that come along with it. It allows faster development because you don't have to develop all of these framework features from scratch, and it allows this nice separation of concerns. And we'll talk about concerns more concretely at the end. So you also remember this picture. Java EE provides a lot of these components that you saw in the earlier picture, and we're using a lot of them. So we're using JPA, JTA, and you'll use the web service facilities of Java EE to implement web API. I now want to give sort of a quick example just to give you a taste of how enterprise Java Beans work, which is the component framework of Java EE. So we said, okay, we have these components. They basically implement a piece of business logic, and then you have dependencies between them. So one service needs to call another service that then maybe does some database operation. So the way that's implemented in EJB is fairly straightforward. So you have some implementation of your service. So in this case, let's say you have a directory of customers and you have a specific implementation that uses an entity manager to store the customer objects into the database. So EJB provides some annotations where you can declare what this service component should be. So in this case, we say this is a stateless component, meaning that it does not store any information across requests. So every time you call the component remotely, it will discard any type of state associated with that request after the request is done. And you've already seen the transactional annotation, which sort of defines a transaction scope. There are other scopes in Enterprise Java Beans and other types of beans. So a bean is in Enterprise Java Beans considered one of these components. And the way that EJB works, it hides the remoting technology completely from the developer, which is very useful because you can develop components very naturally, and then whether they are deployed locally in one application container in one JVM, or whether they're distributed across machines, doesn't really matter for you as a developer. So the remoting is kind of hidden. And the way EJB resolves remote beans is via these remote bean URLs. So it will look up, there's some directory where we know about the bean name or the bean URL and where the implementation is exposed. So under the hood, it will use, RMI or Corba or some remoting protocol. So there are different types of beans, as I mentioned. You have these session beans, which can be either stateful or stateless. You can have singletons, which just means, okay, there's one instance of that particular bean across the entire application. And remoting is hidden from the developer, which is a huge benefit of EJB. There's also message-driven beans, so you can have beans talking to each other via message passing. And we'll talk more about the message passing remoting pattern in lecture 5. So let's look at how this is done in the Spring framework. So a lot of you are probably familiar with it. You've used it in maybe the software engineering and project management course. So you know basically what Spring, parts of what Spring can do. And you're probably familiar with the core container. So you know that you can annotate components as a service, which just means that from the application context, we'll talk about container management in a second, the application context of Spring can give you instances of particular services. And Spring also provides some remoting mechanisms. So you can wrap components via different remoting means. So one way is using the Spring HTTP invokers to have components talk via remoting. And if you have the components sitting in different VMs and you want to have them talk to each other via HTTP, you have to instantiate the components wrapped in these HTTP invoker, either services or proxies. Then when the auto wiring is done by Spring, in the lower example, so in the customer service, the thing that you're getting in the customer directory is not the customer directory implementation, but it's some proxy. It's some proxy that does the HTTP invocation for you. So it's essentially, in remoting terms, this stub we talked about. Why I'm calling it a proxy here is because that's the Java term for what will be returned by Spring. And Spring provides, a bunch of different ways to do remoting. So it hides, for example, RMI for you. It provides a convenient way of exposing objects via RMI, which you know about from distributed systems course. Just to give you an idea of how Spring does things. In Java EE, which you'll be using in the second assignment, so you'll define RESTful web services using the Java EE, specifically the JAX RS facilities. And basically it's just a way of specifying a web API. So you can say, okay, you have this user directory and you can expose it to a particular resource path. So you have these annotations that have this kind of REST API feel to them. So you give a class a path, you give a specific method inside that class a path, and then you can define whether it's a get method or a post method or a put method. You can define whether something is a query parameter or a path parameter. So it's a very convenient way of just exposing your service description as a web API, and then you can use the injection mechanisms that you're familiar with from Java EE. But in all of these examples that I gave, there are some kind of questions that arise when, like, who is instantiating all of these components? So if you just instantiate a component, you're not getting any of the features. who calls who injects the entity manager into the user service, who stores all of the service instances or the entire application state, who knows about that, who manages this connection between the entity manager and the database, who actually runs the transactions, and who serves the HTTP request. And the answer is the application container and the application server. So in Java EE terms, the application server can host several applications. So an application will typically be a web archive file. So it's the analog to a jar file, just in the Java web world. And you can deploy one of these jar files or WAR files into an application server. And the application server will expose an HTTP server for you. It will know certain things about the application. It will know its name. It will know the endpoints it exposes, and then route the requests that come from outside into the specific Java EE application. So there are several implementations of Java EE application servers. TomEE is the enterprise edition of Tomcat, so it implements all the Java EE features, which is, I think, what Spring is actually using in the background as default mechanism. I think if you start the second assignment and boot up and start up Spring Boot, I think it deploys your application into a TomEE server. You maybe heard of JBoss. So JBoss is a term that still floats around. This is now basically it was rebranded into Wildfly, also an application server. And there are a bunch of others. So this is the application server. Let's talk about what container managed means. So I think I didn't add any transitions here, so you get everything in one picture. But on the top left, you see the Spring diagram that we saw earlier with the individual components of the Spring framework. So we'll talk about the core container now. The core container is mostly made up of the application context and the bean factory. So those are the most important parts of the core container. And it implements this dependency injection mechanism for you. So you define an application context in which services live in that application via some configuration. So a typical way is you define the instances of specific services in an XML file, you give them names, you specify which properties should be injected in that bean, and instead of then instantiating them yourself and get unmanaged instances, you let the application container instantiate the beans, which is an instance of a specific service, and then the bean factory will also inject the dependencies of beans itself. So it is responsible for doing this entire wiring process of wiring together the services, injecting the correct implementation. And we'll see later when we talk about programming dynamic features why this is extremely important for other inversion of control mechanisms. So often you'll hear people say inversion of control and say they mean basically dependency injection and conflate the two. I think that's even a statement in one of the Java tutorials. I don't think that's very precise. I think inversion of control is much more general, and dependency injection is one mechanism of inversion of control. And we'll kind of see why that's the case and what other IOC mechanisms there are, but also why dependency injection is such a vital part to enable other IOC mechanisms. So anyway, now you can ask the application context for a specific instance of a specific service, and we'll see later that maybe you don't get the user service impl back, but you'll get some proxy instance back, or you get some instrumented version of that service back. So the application context or the application container manages objects for you, and it potentially augments the implementation with additional features. And this is what we mean when we say something is container managed. So the application container, which hosts the application, knows about the instances and certain concerns of these of the services, for example, transactionality, and then manages those objects for you, and you can get managed instances managed object instances back from the application context. Okay, so let's look at dynamic features and why IOC is such an important mechanism. So before we talk about how we develop dynamic features, it's useful to first look at where these dynamic feature mechanisms are actually useful. If you think about an application, and specifically some service that implements a piece of business logic, the code typically contains not only the core business logic, but also the code that maybe does authorization, logging, invoking the persistence API, and things like that. So generally, when we develop software, we like to isolate these concerns as much as we can. So a concern, if we try to find a concise definition, is some requirement or consideration, and the software system is the realization of a set of different concerns. And there are different types of concerns. So we say a core concern is something, is a core functionality of a module. So this would be a business logic. And around that, you have these cross-cutting concerns, which are on system level. So these are peripheral requirements that basically all other components or modules have. So authentication, security, transactions, auditing, profiling, those are all concerns that modules need to implement, or need to use rather, but we'd like to kind of separate them. So we'll see how we can separate these cross-cutting concerns via decomposition, modularization, and this elusive inversion of control mechanism. And a technique that we need to use, or that we need to learn about before we can do this, is metaprogramming. So metaprogramming is basically the ability of a program to treat other programs as its data. So to look at them, analyze them, introspect them, maybe even modify them at runtime. And this is like a fundamental mechanism to implement dynamic features, because you need some dynamic way at runtime to analyze a program or maybe modify it. In Java, there's two main streams of metaprogramming. So one is reflection, which is basically a non-intrusive way of metaprogramming. So it's the reflection API in Java provides this object-oriented meta model, provides a meta model of the language itself. It provides these reflection mechanisms. We'll see them in a minute. Annotations that you've worked with before, like annotating JPA entities, is a form of reflection mechanism, and we'll talk about dynamic proxies as well. The more intrusive way of metaprogramming is instrumentation. So when we talk about instrumentation, we can mean different things. In this particular case, we're talking about bytecode injection. So we'll see that. So let's have a look at reflection. So you've all used reflection. Reflection is just a way of inspecting certain aspects of the program at runtime. So even just checking at runtime the class of a specific object can be considered as a reflective mechanism. So this instance of and this class keyword in Java are reflection mechanism. So introspection gives us the ability to analyze the program and its structures at runtime, which is required for a bunch of different applications. So contextual IDE support is, so a lot of IDE stuff can be done statically. But if you recall the lecture 1 where we talked about object relational metadata mapping, that is something where when the program starts up, the program will analyze the entities, look at the properties, and so forth. So we can inspect things like classes, their names, interface hierarchies. We can inspect fields of a class, so their types and the names of fields. We can inspect methods and constructor signatures, so we can again find the names of methods and the argument types and their return types. There are a few things you can't inspect very well in Java, which are parameter names of functions, because they are often discarded during compilation, and generic type parameters of variables. So if you define a variable that's a list, and that list has some generic type, then that type will be lost during runtime, which is this Java type erasure. So you can inspect a generic type parameter of a class definition, that often works, but of a specific instance, you often can't reliably. So for example, Java or JPA often needs to check the type of a list, so it needs to know what types are in that list, and the way it does that is it often just peeks into the list, checks what type the first object in the list is, and then associates that type with that list. So there are ways of getting around it, but they're not like fundamental concepts in the reflection API. So let's look at some examples in the Java Lang Reflect API. So what you can do is you can get the class object of a specific class. So you've seen this before. There's a concept in Java called class. So it's literally a class that's called class. And instances of that class encapsulate details and the information of a particular class. So in this case, we're assigning the class object of our money class to this particular variable that we can't call class with SS because it's a reserved keyword. And then we can get all of the declared methods in that class, iterate over them, and spit out their names and their parameter names. And this would be the output for the money class that's in the template. So remember, there's a currency field, and there's getters and setters for that. You can already see that the argument name of the set currency method is discarded. So the name of the argument is now arg0 and no longer currency. And you can also get the inbuilt methods like the toString and the hash code that we override in the implementation. So essentially, the Java Lang Reflect API gives you a meta model of these object-oriented concepts. So it gives you classes that are called class, method, field, or constructor, and that you can then programmatically use in a program to analyze a class or another program. So as I've said, this is useful if you recall a metadata mapping problem. What we can do now is we can inspect the person class at runtime, extract all the fields, and then dynamically create this column map at runtime. So there's no need to define that statically. You can just create that with reflection mechanism. The other, what you also want is to actually dynamically invoke stuff. So it's one thing to inspect, another thing is to actually do something on with the program. So the first thing that comes to mind is instantiating objects dynamically. So if you have a class object that encapsulates some other class, you can dynamically create an instance of that class by getting all the declared constructors and then calling new instance. So those are actually methods of the Java Lang Reflect API. Passing no arguments to the getDeclaredConstructor method means that you get the default constructor. It has arguments for types, so you can pass other class objects to the getDeclaredConstructor method, and then you will get the constructors with that signature. So for example, if you have, if you say new money, and there's a money constructor where you pass a string as the currency, then you would have, you could get that constructor by calling getDeclaredConstructor and passing the string class as an argument. And you can do the same with methods. So you can iterate over all the methods. Let's say you want to get the setter for the value of the money, so it's a big decimal, and you find this set value method with the big decimal as a function parameter, And then you can invoke that method simply by calling invoke, which is again an API construct, on this method object. And then, because you're not calling that on the object directly, you need to pass the object that you want to invoke the method on. So this relies on you being nice and not naughty and passing some object that's not from that class and does not have that method. So you can, you can break code like this by passing some object that does not have that particular method, and then something will explode. And then you pass the arguments of that method invocation. So you can see why this is useful, because now you can kind of dynamically invoke things at runtime. You can delegate invocation, and we'll talk about, we'll see an example later why this is useful for inversion of control, or why this is even essential for inversion of control. And you can also do field access dynamically. So you can iterate over declared fields, and you can set them or get or set them dynamically. So you can access field objects. In Reflection, you can also access private static final fields, which is a bit strange the first time you think about it, because you think, okay, something's private, so you can't see it. Something's final, so you can't change it. You can with Reflection. There are some constraints introduced in Java 9. So with the module API, I think there's additional security constraints with which fields you can make accessible, but it's not really relevant for our assignment. Okay, so in summary, we can do this runtime invocation of methods. We can create new instances via new instance. We can invoke methods with the invoke method, and we have runtime access to member variables. So I want to talk about dynamic proxies because they are a very low-level way of implementing inversion of control mechanisms. So you've heard about the proxy pattern. Essentially, on the most generic way you can visualize it, you have some subject that basically it's a contract, an interface that gives you some method signature. There's a real implementation of that, which is the real subject, and that would contain the implementation of that contract. But the client that invokes the subject doesn't actually invoke the real subject, but it involves some proxy instance that claims to be or looks like the subject. So it implements that interface, but it doesn't actually contain any implementation code. It contains some other code that then calls the invocation handler, and the invocation handler calls the actual real subject. So this is not like, this is a pattern, right? So this is something you need to implement. But the idea is that a proxy has associated with it the interface, so it looks like the interface that it's proxying, and it has an invocation handler which does the actual invocation. So the proxy is like just a generic vehicle, and the invocation handler actually implements some logic. So the logic that I want to use as an example is this way of executing transactions. So let's say you have this invocation handler that executes a transaction in a generic way. So we've seen this, you typically have transaction is made up of like 3 calls. So you begin the transaction at the beginning of some method invocation. You invoke the methods which execute the database commands. Then you want to commit before you return whatever value that business logic may return. And in case of an exception, you want to roll back. So this is like the archetype of a transaction. So it's kind of natural to generalize this with an invocation handler, because the invoke method of an invocation handler can basically invoke any type of method dynamically. So you can now wrap the method invocation of whatever business logic you have with an invocation handler and wrap that with this transaction mechanism. So now instead of calling the real user service, which implements the logic and calls the database and everything, you're creating a proxy instance that looks like the user service. So the proxy and the proxy new instance, or new proxy instance are again methods, are classes and methods from the reflection API. You pass to that new proxy instance method the class loader. Let's not worry about that right now. You pass the classes that you want the proxy to look like. So typically those will be interfaces. You can add multiple interfaces. And then you add the transaction handler and the invocation handler, which is invoked every time some client invokes a method on that user service. So let's say the client is calling service.addUser or something. Instead of calling the real user service, the invocation handler invoke method is called. The proxy object is passed to the invocation method. The method that's being invoked, this dynamic runtime object that encapsulates the method, is passed to the invoke function and the arguments of that method. And now you can, wrap the method invocation with whatever magic you want, and then call the method invocation, invoke the method at whatever time you see fit. You can actually just swallow a method invocation. You can just do nothing in this invocation handler, and invocation will just get lost. And if you think back to what I said about container management, you can see why it's important that you have these container managed objects, because if you request a user service from the application context, you may not get the real user service back, but you'll get this proxy instance back that does some additional magic. And in some way or another, any type of application framework will give you that where you can add additional functionality, like a transactional, like these transaction boundaries. It will return, the application context will return some modified version of the actual service, whether it's a proxy or whether it's an instrumented version of the object. We'll see about instrumentation next. You need some way of getting these container managed objects from some application context. So in this case, the user service would be, we would get back a container managed proxy. Okay, so I know this is sometimes it's a bit difficult to wrap your head around this the first time, but dynamic proxies are a really important part and concept in application frameworks, because it's, as I said, such a fundamental mechanism to achieve inversion of control. And here you can really see inversion of control in action. You're not, the user service, the real user service implementation isn't calling the user transaction anymore. You have this inversion of control in that the control flow is no longer flowing from the user service to the transaction, but you have this transaction handler which now calls the user service rather than vice versa. So this is why we say inversion of control. So, and this is also a good example of why I think it's not useful to conflate inversion of control with dependency injection, so saying that they're the same thing. Because there's no dependency injection really happening here. This is like pure inversion of control. Okay, so in the Java Reflect API, there are some additional higher level concepts. The Java annotations are part of the Reflect API, so there's syntactic metadata, you know about them. And there's this concept of Java beans, which are the language-specific conventions for data classes, and we'll look at them. So annotations, you know, are just this metadata that you can place on top of types or fields or methods, and they have some properties that you can set. So in this case, the colon has a name and has a unique flag or something. If you look at the implementation of that interface, or sorry, of that annotation in the JavaX persistence API, you can see that there's this additional keyword with @interface, and that specifies that this interface is actually an annotation. And now you can add types and attribute names and default values for those attributes. The two main things about annotations are the retention policy and the targets. The retention policy specifies when the JVM, until which point the JVM keeps this metadata information. So in most cases, you want the information at runtime. So for all these dynamic application framework functionality, you typically want to keep them in at runtime, but there's also possibilities to discard them at compile time or discard them before the application starts. There are different use cases for that. And the target annotation specifies where that annotation can be placed. So in case of the column annotation, we can place that on top of methods and fields, but not on top of types, for example. So annotations are this syntactic metadata, and they have these annotation. You can specify the annotation target, and you can specify the retention policy. You'll implement your own annotations in the second assignment. Actually, the interface is already there, but you need to assign them specific retention policies and annotation targets, and you'll use them for implementing your own dependency injection container. And if want to talk about Java beans just very briefly. Java beans are, as I said, this language-specific convention that you have a private attribute with a specific name and a specific type, and then you have public getters and setters that relate to that property. So if you have in this money class, you have a currency attribute, and you have setters, getters and setters that are called get currency and set currency. And you can kind of see in your IDE that when you have something like this, it will group the currency, it will create this new virtual kind of thing, this violet icon with, I think it has a P inside, so it's a property, and group together the attribute and the getter and setter with it. So this already shows you that there's some concept in there, and this is what we call a bean property. And there's an additional API in Java, which is called Java Bean. And this API gives you an introspector that's sort of a high-level way of getting information from a class. So you get this Java-specific or these Java convention concepts back. So you get a bean info, which is just encapsulates the information about this class, and it's interpreted as a bean. And you can iterate over these property descriptors. And you can get the field that's associated with that property, and you can get the read method and write method in kind of a convenient way. Okay, so in summary, reflection allows a program to inspect itself or modify itself, invoke itself. So it's a meta model for the programming languages. In Java, it has concepts for a class, for a field, a method, a parameter, or constructor. And there are additional high-level concepts, depending on the language. And in Java, there's this language convention with the Java beans, and you have the annotations that specify this metadata. In Python, for example, you also have this funny @ symbol, but it's not a annotation in the same way that it's just a metadata in Java. It actually does something to the method, so it's a decorator of some sort. So actually, you can use these @ symbols in Python to create dynamic proxy mechanisms. So the problem with reflection, obviously, programs become more difficult to understand because you don't have a classic control flow anymore where you see specifically which method is invoked on a specific object. Rather, you have this dynamic, method object. You don't know which method that's actually referring to. You say invoke, you don't really know which method is invoked, and so forth. So the static type checking is lost, which is consequently you have a higher risk for errors. So there's a reason we have static type checking, and that is kind of lost through reflection mechanisms. Okay. So let's talk about instrumentation, which is the more intrusive way of metaprogramming. In essence, the Java compiler takes a Java file and creates a class file out of that. And the class file contains bytecode. You can disassemble a Java program with JavaP command. So it's in the JDK, so you can execute that. And you can, for example, you can compile the first assignment, go into the classes directory and call JavaP on the money class, for example, and then you get this representation of the bytecode. So you can see the class definition, you can see the method definitions, and you can see the actual VM commands that are executed when or that implement this specific method. And when Java loads a class, it does this dynamically. So it loads these class files dynamically at runtime. It actually lazy loads them, so it loads them the first time you use them. And the JVM then executes this bytecode once you invoke the classes or some code is executed in the class. And basically we can hook into every step of this pipeline. So we can inject additional code to the Java file before it's even compiled. After the Java program has been compiled, we could inject bytecode into the class file before it's loaded. And as the class file is loaded, we could again inject bytecode into that class. So why would we want to do that? We will see some examples, and there's two ways of doing that. So one is the dynamic instrumentation, which is basically performing this instrumentation at runtime, so during the execution of a program, or statically, so before the compilation or inject after the compilation. You'll be using the dynamic instrumentation in the second assignment. So you'll implement a framework feature where you need to inject specific, so a bytecode pattern before a method and after a method. And it really sounds like pretty scary when you hear about this the first time. Oh my God, you need to inject bytecode. You don't need to write any bytecode. So the way that Java facilitates bytecode manipulation is via two things. One is the instrument API. So Java API has these high-level concepts for this instrumentation process. So it has additional concepts for a class loader, which you can modify, which loads classes. It has this idea of an agent that is started with your JVM that can transform class files. You have this interface called the class file transformer, which is past the classes that are loaded by the agent. And then, as the class loader loads the classes, it calls the agent before it passes the classes to the JVM, and that gives you sort of a hook to manipulate the bytecode. And I promise that you don't have to write bytecode. You will use Java Syst, which is a framework for generating bytecode from higher level concepts. So you have these additional meta model concepts, which are again called like class and field and method, and you can programmatically create things like a field or a method, and you can create Java code as strings and then use Java Syst to compile that into a bytecode and then inject that into the class at runtime. No bytecode necessary. Okay, so the way that this is used, or this can be, so the things that we talked about, reflection and bytecode manipulation and also dynamic proxies, are very low-level ways of implementing dynamic features and facilitating inversion of control. Aspect-oriented programming is a programming model that elevates this as sort of a first-class citizen and gives, and as AOP implementations like AspectJ give you high-level tools to achieve this injection of dynamic features without having to muck about with dynamic proxies or reflection mechanisms or bytecode instrumentation. So it all hides that for you while giving you high-level concepts to work with and create these concerns. So let's break down some of the terminology of AOP before we get into specific implementation. So you remember this picture? We said that, okay, a system is made up of different modules, and the modules is made up of different concerns, and we kind of want to separate those concerns. And you saw in the, even though I'll show an example later. So the loose definition of an aspect is sort of the realization or the implementation of a cross-cutting concern. So it encapsulates this concern into a module, and that is then that contains all of the code associated with that particular cross-cutting concern, and we call that an aspect. In a concrete example, let's look at like a banking application again. Let's say you have different modules. You have an accounting module. You have a module that does the ATM codes or bank or money withdrawal, and you have some money transfer module. And those will invoke the transaction module. So you have some transaction API. This is just an analogy. You have the transaction API JTA, which provides this user transaction interface for you. And in your transfer money module, you have a method called transfer money, where you begin the transaction, you commit the transaction after you're done with your business operations, and in case of an exception, you roll back. So this is like the cross-cutting concern. You can see that this concern of running the transaction will be implemented in all of the modules. So they're cross-cutting, and they always kind of look the same. You always run the begin at the beginning of the method, you always run commit after the method is done, and you run rollback in the case of an exception. So instead what we want is we want to further separate that concern into an aspect, and then have this aspect automatically woven into the invocations. So in our example, what we want is we want to free the transfer money function of any type of API invocation of this transaction API. We need some way of specifying that this transfer money, the transaction aspect should be woven into the transfer money function. There are different ways of defining that. A typical way is defining additional metadata so that developers have a convenient way of saying to the application container, look, this is a transactional method. I want this to have the transaction aspect. But you could conceive that you could define that in some XML or some external configuration. And then instead of, you have this inversion of control mechanism again. So instead of having the transfer money method calling the transaction API, you have some mechanism that calls the transfer money function and wraps the function invocation with this transaction procedure. The question is now, as before, how does the function actually get passed to the transactional method invocation? So you have, in this case, you have some callable which encapsulates the method, or sorry, which represents the method being invoked, and then you wrap and call the function again. So it looks very similar to the dynamic proxy example that we gave before. So this is technically not what we mean when we say an aspect. We'll, in AOP terms, we'll look at that in a second. Okay, so the main concepts of AOP are these aspects, which is a modularized implementation of this cross-cutting concern. So you have the transaction aspect, which implements all of these transactional mechanisms and a way of injecting the transactional aspect into the modules. A join point is a point in the execution of the program where you could execute a specific piece of code. So a point, we'll see examples of join points in a second, but essentially there are things like method invocation or access to a field or calling a constructor. So those are points in the control flow where you could do like funny stuff around it. A point cut is an expression. It's a concept that expresses a set of join points. So point cut could be, give me all methods that have this name and then this signature. And that will give you a set of join points around method executions with that name and that signature. We'll see some examples. And then you have the advice, which is the actual code executed at this specific join point. So in our case, the advice would be the transactional advice that's executed around a function. You can execute an advice before a join point or after or around a join point. So the join point in the previous example would be the execution of this function. So let's look at this example and sort of break down what different join points there are. So this is like a naive implementation of an atomic integer. You have some field that contains the counter, and you have a lock that provides mutually exclusive access to this critical section. So the low-hanging fruit join point is the constructor. When the constructor is called, you can execute an advice. So you can say, execute this advice before the constructor, or after the constructor, or around this constructor. There's the actual function execution. In the case of this lock, you have a field read access. So you're reading the field that refers to the lock objects, and then you call some method on that object. So those are two separate join points, the read access and the call join point. Here again, you have a field read access when you get the counter and assign it to this temporary variable, and you have a write access. So those are again two different join points, which you can execute aspects around, or sorry, advices around. And then you have the exception handler, and a join and a point cut for exception handlers could, for example, include the specific exception that needs to be thrown for the join point to, or the advice to be executed. And then you have the return statement, which is sort of the end of the function. Okay, so what's the difference between a call and execution? That's all sometimes confused. So a call matches before or after a method is called. So you're still in the scope of the caller. So in this case, the caller is the get and increment method, and the thing that's being called is the lock method or the release method. So you're still in the context of the caller. And execution matches when the method starts to execute. So you're already in the scope of the callee. So in the execution, you would already be in the scope of the get and increment method. Okay, so those are join points. Now, how do we express which join points we want to attach our advice to? And this is what we mean when we say point cut. So there are different ways of defining point cuts in AspectJ, but basically there's this. So you'll use AspectJ for the second assignment, which is a particular implementation of this aspect-oriented programming model in Java. So there are things called named point cuts. So this just means that you have an expression, much like a named query. So you have some expression, and you give that expression a name. So you can later refer to that expression more easily. So the point cut name in this case would be, give me all operations that operate on some account object. So the account would be like a concept in your application, and you want to specify a point cut that captures any type of call, any type of method call that has as signature that takes as an argument an account object. So if we go from left to right, you have the access specifier of that point cut. So you can say that a point cut is public or private. Point cut is just the keyword. So you'll see in AspectJ you have additional syntactic constructs, and aspects will be defined in their own syntax. And there are IDE plugins that allow syntax highlighting and give you a compiler for these aspects. So point cut is the keyword. You say the point cut name, and then you have the point cut type. So we talked about these different point cut types, like call, execute, field read, field access. And in case of the call or execute, you want to specify the signature that matches that particular call. You can also define aspects and advices just in plain Java, and the AspectJ provides like a Java-friendly API to do that. So you can define a point cut as just a method. So the method would be the name of the point cut, and the expression, so the actual point cut would be defined in like a string in an annotation. Okay, let's look at some point cut examples. I don't want to go into too much detail because you'll be working with that in the assignment. But you can, if we look at, okay, so we want a point cut that specifies a particular method execution. So you use the execution point cut type, and then you specify the signature of that execution. So the first example is very specific. It only matches this very specific signature. So it matches the setX method when it's called on the myClass class. It only matches the signature if it returns a void and takes an int as input parameter. We could make that more general with a wildcard argument. We could say, okay, give me all methods that are called setX and take an integer. So that would match all of the classes or any type of method that has this name attached to it. In general, when you write point cuts, you want to be as specific as possible. Why? Because the advice that's injected or woven into the specific join point that the point cut matches will be, so it's woven into all of those methods. So potentially you're generating a lot of extra bytecode, and you may have, undesired behavior because some method that you didn't think of when you wrote the point cut will have this additional behavior attached to it. So it's important to write like minimal matching point cuts for several reasons, one of them being the ones I explained. So we've already seen this example with the call. It's very similar to the execution point cut. You can specify a point cut when the target object that's being operated on is of a specific type. I gave this example with the execution handler earlier. The handler point cut type specifies when when a specific exception handler is executed on a specific type of exception. And you can have things like compositions. So you can have conjunctions or disjunctions, or you can have negations on point cut expressions. So you'll implement two simple point cuts in the second assignment. Okay, and the advice is basically, as I said, just this piece of code. So you can think of it as a class and a method implementations that are injected into the point cuts that you define. So, and as I've mentioned, you can run an advice before, after, or around a function invocation. So if you use the around way, you get this additional concept of proceed. So there's another function that's part of the AspectJ API, which basically just executes the join point that your advice is executing on. So analogously to the dynamic proxy example where you run method.invoke, here you call proceed, or in the case of the example that we gave with this transactional method where you pass the callable, it's very similar to that. So in the case of the callable, you have you just invoke the callable, and here you say proceed. But it's the same idea. All right, so there are different times at which the advices are woven into the specific join points. Generally, weaving refers to this process of merging the aspects into the program code. And there are four principal methods. So there's compile time weaving, which means that we compile from source and produce woven class files. So that basically means we, at the time of compilation, we weave the aspects into the advices into the class files. There's post-compile or binary weaving, so which means that we weave code into existing classes or jar files. So this is useful when we don't have access to the source code and want to modify like third-party classes or jar files. There's load time weaving, which basically just deferred binary weaving. So we weave the code when we load a class. This is basically what you'll be doing with the bytecode instrumentation assignment 2. So it's not called weaving in the Java-Lang instrument world, but it's the same idea. So you inject bytecode at a specific point in the pipeline, and load time weaving refers to, in Java-Lang instrument terms, when the class is loaded at runtime. And this is what AspectJ does. There's also this runtime weaving idea that instead of actually intrusively injecting code into already created classes, you have runtime you have non-intrusive weaving that's basically just a dynamic proxy. Dynamic proxies are used in a lot of situations in different kinds of frameworks. So for example, in JPA, in some situations where you get a collection of objects that are read from the database, you don't actually get a specific instance of that collection back. So when, let's say you have a list, you have an entity that has a list of some other entities as dependencies. And when you first load that entity, if you don't have eager fetching enabled, you'll get a proxy instance back. So it's not an array list or a specific collection, it's some proxy that is then lazily loaded at runtime when you first invoke some operation on that list. So runtime weaving basically just refers to this use of dynamic proxies. And as one of the theory questions for assignment 2, you'll see that you'll need to think about when to use which weaving method, when it's useful to use which method, what the benefits and drawbacks are. Okay, so it was a lot quicker than last time. This is already the conclusion of this lecture. So here are some of the resources and credits. So I used a lot of material from previous years of DST. There's an excellent documentation on distributed transactions in the Oracle documentation. You can get the OAuth spec from OAuth.net. It's a very convoluted specification. It's hard to read, at least in my opinion. And this was the Philip de Rijk is like a security expert that was talking about OAuth. So I recommend watching that talk. And then, you know, there's a bunch of AspectJ programming guides and books. Okay, so this concludes the lecture. If you still have questions, I'll hang around for 5 more minutes or 10 more minutes to answer any questions that you have. But that concludes the lecture.